Okay, so this is the section that I've been talking about for the last couple of days. Every time that we go to take a derivative and I tell you, no, we don't have a rule for that yet because you've got a function plugged into another function, you've got a composite function, a nested function. I've said a number of different things, but there are different functions that we've had that we were not able to take the derivative of yet because we had one function plugged into another function. So learning the chain rule will open up just huge amounts of functions for us. So composition functions. This is our notation. Remember that f and then compose with g. Oops, didn't mean to draw there. And then this is f of g of x. So this way, the way that it's written right here, is what we're going to kind of reference here. So f of, and then inside of my function f, I plug in an entire new function. So like in sine of x, for example, instead of just having an x plugged in, maybe I have an exponential function. Maybe it's like sine of e to the x. So all of these examples down here, in example 1, these are all examples of composite functions, like one function plugged into another function. So we will call f of x the main function. So that's kind of, we will also call it the outside function. So either the main function or the outside function. And then g of x, whatever got plugged in instead of just an x, we will call this the nested function. Or again, the inside function would serve the exact same purpose. So outside and inside, main and nested. I like main and nested because like nested, you picture it as being nested inside of something else. So this first example right here, we're just going to take it nice and easy, just figure out, okay, what's the main function, what's the nested function? So if this is supposed to be f of g of x. So this one, of course, this lesson is better suited when we're all in class in person. I can ask you guys out loud, what's the main function, what's the nested function? So if you're feeling really ambitious, I don't know, maybe you pause the video, try to come up with it yourself. So this one, cosine is kind of your main function. It's normally just a cosine of x, but instead of plugging in just an x, there's this x cubed in its place. So f of x, the main function, is a cosine function, and we just write x, because normally in our original cosine function, we're used to just seeing an x there. But our nested function, instead of plugging in an x, we actually have an x cubed plugged in there. So cosine is the main, x cubed is the nested, or again, outside, inside functions. The function, like I said, I like the term nested because you can see that it's physically nested. It's nested inside of another function. It's what got plugged in instead of just an x. Here, our main function is a square root function. So square root of x, but it's not square root of x, it's actually the square root of x to the fourth plus 1. So our nested function, the one that's physically plugged into another function, is an x to the fourth plus 1. So if you were to do your like algebra 1 style f of g of x, we'd replace the x with an x to the fourth plus 1, and we would have this function. This one's a little bit tricky. Secant squared of x, remember I told you guys about that trig notation? This is actually secant of x quantity squared. The reason with trig that we write the squared on the inside like that is because if the squared was right here after the x, we would be confused as to whether it was this secant quantity squared or the secant of the expression x squared. So they put it in here just to avoid confusion, but it's really this anytime you see it. So our main function is a squared function, like an x squared, or another variable squared if having x's everywhere is confusing you. And then g of x is what got plugged in instead of just an x. So instead of just squaring an x, we're squaring a secant. So the nested function is actually a secant function. All right, second to last example here. Our main function is a tangent function. But instead of just having an x plugged in, we have this quotient. So that quotient is our nested function. Okay, so again, algebra 1 style, if you were to practice plugging one function into the other, f of g of x, if we replace this x with the expression x over x plus 1, we would have this function right here. And last of all, our main function is some variable to the fourth. So that is f of x is x to the fourth, but I don't just have an x, I have this whole quantity right here, and so that is my nested function, the expression x squared plus 3. So now anything in this category, with the exception of part C, we are not able to take the derivative yet. A, B, D, and E have these nested functions and we have no way to simplify them up. Part C, we have taken the derivative of something like that before just by writing secant times secant and then doing a product rule. But with these four, there's no way to rewrite them. So up until now, we had no way to evaluate expressions like these four right here. Example 2, I meant to change this when I was typing. I don't want to do this polynomial squared. I actually want to do sine squared. All right, so we're going to find the derivative of sine squared by expanding. So by expanding, I mean writing it out twice, foiling it, using the product rule, kind of like what I was just talking about with part C. So by expanding, that means that we are going to write, it's like y equals, instead of sine squared, we're going to write sine x times sine x, which is exactly what sine squared means. It just means sine multiplied by itself twice. And so when we take the derivative, y prime, or we could write dy by dx if we liked the other notation, we do a product rule. So we do the first function, so this is going to be your function u in the product rule. This is going to be your function v. So over here, u prime is the derivative of sine, which is cosine. And then v prime is the derivative of sine, which also is cosine. And so when we type this, or write this all out, get the derivative, the product rule, we have the first function, u, which is sine x, times the derivative of the second function, so v prime is cosine, and then plus the second function, which is sine, and then times the derivative of the first function, so u prime is cosine. So now you'll notice the variable parts are exactly the same. I have two of these. So this is 2 sine cosine. Make sure that when you're doing trig, you actually have an input. You have sine of x, because if it doesn't have the x, it's just 3 letters. Doesn't mean a thing at all. Okay, so now try to take the derivative using the power rule. We're going to kind of walk our way through what the chain rule actually means. So keep in mind what we wrote for part C. Sine quantity squared is actually this, like sine x in parentheses and then squaring the entire quantity. If we attempted to take the derivative using the power rule, what we would do is for y prime equals, we're going to put a question mark up here because we're just testing things out. We're not entirely sure that this is the derivative. Normally, according to the power rule, we would take this power right here. We'd throw it out front as a coefficient, so we would have a 2 right here. And then the power on sine would drop down to a 1. And so this, we don't like that form, so we're just going to write 2 times sine. Alright, so when it's written out like this is what some of you guys were trying to do when we were working on the notes from the trig section, is you guys would say like, well, why can't I just move the 2 out front? That's the power rule. And so if all you do is move the 2 out front, this is what we're left with. This is what the derivative is supposed to be. We did this out the long way. We did the algebra, we did the, u times v, sine times sine, and this is what we got as the derivative. This is the actual derivative. This is not. This is what we get when we attempt to use the power rule. Well, what's missing? What's missing is, here's what I have here. I'm missing this factor of cosine. All right, so what's missing is a factor of cosine. So my derivative is supposed to have a cosine x, because I know that this right here is my answer. My derivative, if I do just the power rule, doesn't have a cosine x in it. So again, this is the part where normally, if we were all together in class, I would ask you, well, why cosine? What is cosine? So I challenge you, maybe take a couple seconds, think about it, see if we can figure out what cosine is, what does it mean, how does it relate back to my original function. All right, so think about it. Are you thinking about it? Okay, if you guessed that cosine is the derivative of sine, you were right. Okay, so what that is now sine is the nested function, if you look at it like this. So when I have my inside function, my outside function, sine is the nested function, and this extra factor of cosine was the derivative of sine, which is the nested function. So the missing factor was actually the derivative of the nested function. Okay, so the derivative of the nested function, we're going to call this the correction factor. So we will refer to this as the correction factor. So the correction factor, again, is the derivative of the nested function, or the derivative of the inside function. We need it to actually get the correct derivative. Because when we have a nested function, we can't just use our old rules, like the power rule or the product rule or whatever. We can use the old rule, but then we have to make sure to throw in the correction factor. So say I had just thrown the 2 out front. It'd be 2 times sine, be like, oh, I'm missing something, the correction factor. What's the derivative of sine? Cosine. And that's how you would land with your actual correct derivative. So if we flip over here, we've got the chain rule. So here's what we are going to write down. So the chain rule formula, here it is. So we have, and let's write this down kind of piece by piece. So if I'm taking the derivative, so d by dx, if I'm taking the derivative of a composite function like this, here's what I do. I take the derivative of the outside function, I leave the nested function in place, and then I multiply by the derivative of the nested function, which, like I said, we are calling the correction factor. So let's write out some pieces here. So this part we are going to refer to as the derivative rule. And this part right here is the correction factor. All right, so the derivative rule and the correction factor. So if we look back at that previous page, here's my derivative. This is what the derivative is supposed to be. Here's the derivative rule. And the derivative rule, by that I mean taking the derivative of the outside function. The derivative of the x squared is 2x. So that's where the 2 sign comes from. And then times the correction factor, which is the derivative of the inside function. So let's practice that a couple times. So example 3. We want to find the derivative of this polynomial right here. Now, in algebra world, this would be absolutely terrible, but we could write the 7x minus 9 out 5 times, FOIL it, simplify it up, then take the derivative. That would be horrible. Makes me want to cry a little bit. But if I do the chain rule, which I have right up above, f prime, I start with the derivative rule, which is, as of a week ago, exactly what you thought you could do, which many of you thought, well, yeah, I can just bring the 5 out front and then drop the power down to 4. And you thought that's all you needed to do. But we know now that we're supposed to have this correction factor, and the correction factor is the derivative of the inside function. So my inside function is a 7x minus 9. It's linear, so its derivative is a 7. So I multiply by 7, simplify this up, 5 times 7 out front gives me a 35, and then times the quantity 7x minus 9 to the 4th. Definitely beats writing that out 5 times and foiling it. All right, so technically, the chain rule, we've been doing the chain rule all along. So say, for example, if I wanted to find the derivative of cosine, here cosine is my main function, and then we can consider x to be my nested function. So if I wanted to take the derivative of this, the derivative of cosine is negative sine, and then I leave my nested function of x in place, and then I multiply by the derivative of my nested function. The derivative of x is 1. So I end up with negative sine x, which is what I've known to be the derivative of cosine. So technically, we could be considering ourselves to do the chain rule all the time because x is always our nested function, and the derivative of x is just 1. So let's do this again. Sine squared, so using the chain rule. Remember, sine squared is actually sine of t, quantity squared. So when I take the derivative, f prime of t, I do the derivative rule, which means I do a power rule where I throw the 2 out front, drop the power down to 1, and then I have to multiply by the correction factor, which is the derivative of my nested function. My nested function is sine, its derivative is cosine. So let's clean this up a little bit. So I have 2 times sine to the first, which of course is just sine, and then times cosine. Okay, so there's my derivative, same derivative that I got on the front. Okay, so now these ones are all just nice little chain rules. So this one, my outside function is cosine. My nested function is a 9 theta plus 41. So if I'm finding y prime, I start with the derivative rule. Derivative of cosine is negative sine. So negative sine of, leave the 9 theta plus 41 exactly where it is, and then times the correction factor, which is the derivative of the nested function. 9 theta plus 41 is linear, so the derivative is 9. So simplify that up. Now I have a negative 9 out front, times the sine of 9 theta plus 41. So that is the derivative of that function. Next function, my main function is e to the x, the exponential function. My nested function is the 2x squared that I have plugged in here, where there's normally just an x. So for the chain rule, I start with my derivative rule. Well, the derivative rule, derivative of e to the x is e to the x. So I start with the best derivative ever. And then I multiply by the correction factor, which is the derivative of my nested function. My nested function is 2x squared. The derivative of 2x squared is a 4x. So simplify this up. Normally you do algebraic functions first, and then you write the exponential functions, so that's just the typical order that they should go in. Okay, next one. This one's going to be nice. So this, underneath the square root, this is x plus 1 to the 1/2 power, and then over an x plus 2. So this, we've got a quotient rule, and then inside the quotient rule, we have a chain rule. All right, so we're going to simplify this up. So let's do high is x plus 1 to the 1/2 power. Low, of course, is just an x plus 2. D high, I have to take the derivative of this using the chain rule. So I start with my derivative rule. The 1/2 comes out front. The power drops down 1 to a negative 1/2. And then I multiply by the derivative of the nested function. The nested function is an x plus 1. The derivative of x plus 1 is 1. So that is my derivative of the numerator. And then d low, the lower function is x plus 2. It's a linear function. Its slope is just 1. All right, so let's combine all this up using a nice quotient rule. So y prime equals, we've got low d high. So we multiply this whole thing out. So we've got 1/2 times x plus 1 to the negative 1/2. And then low is x plus 2. And then minus high d low, so times 1, of course, just stays the same. So I have an x plus 1 to the 1/2, and then all of that over low, low. So x plus 2 quantity squared. So we should be able to clean this guy up a little bit. So this piece right here, the negative 1/2, means that it's a square root flipped into the denominator. So this is, we have an x plus 2 over 2 times the square root of x plus 1. That's this piece right here, simplified up a little bit. And then minus the square root of x plus 1, all of that over x plus 2 quantity squared. So again, clean this up a little bit. This guy right here, we need to get a common denominator in the numerator so we can combine them up. So starting with this piece, the root x plus 1, I want to give this a denominator of 2 times the square root of x plus 1. So multiply top and bottom, so I can at least combine those two up. So I get an x plus 2, and then minus, when I multiply this out, the x plus 1 times x plus 1, the root x plus 1 times root x plus 1 gives me an x plus 1, and then I'm multiplying by this 2. Don't forget about that. So I get 2x plus 2, and then over my common denominator of 2 times root x plus 1, and then all of that is over this denominator of x plus 2 quantity squared. So this is all just algebra. We're almost done, actually. So this equals, when I subtract these things, the 2 minus 2, those cancel out. I have x minus 2x. That gives me a negative x. And then over, now here's what's going to happen. The 2 times root x plus 1 is in the denominator. And then when I divide by this, I'm technically multiplying by the reciprocal. So the x plus 2 quantity squared ends up in the denominator as well. And that is my beautiful final answer. All right, so we're going to do the next two problems. We're going to do 6 and 7 as well, and then we're going to call it there for day 1. So find the equation of a tangent line. So tangent line, let me write this up here. So y minus y1 equals the slope, and then times x minus x1. So the x1 is given to you for free. That is this value right here. Don't think of theta as being anything weird. It's just an x. It's just your independent variable. So I'm using the pi over 2. So to get my y value, I plug it right into the function. So f of pi over 2. So that is sine of cosine of pi over 2. So think order of operations. Start from the inside and work your way out. So starting here, cosine of pi over 2, that's 90 degrees. That's the x value for that angle, and that's just a 0. So this is sine of 0, because again, the cosine of pi over 2, we evaluated that, it came out to be 0, and the sine of 0 is just 0. So that's the y value. Next, I need to find the value of the slope. So I need to find f prime first. So here's my original function. My outside function is a sine function. My nested function is a cosine function. So when I do the derivative rule, the derivative of sine is cosine. So I have cosine of, and I actually leave the cosine theta in place. I leave my nested function in place, and then multiply by the derivative of my nested function. That's the correction factor. So times the derivative of cosine, which is negative sine. Okay, so that's my derivative. No need to simplify it any further because I'm just going to plug in the pi over 2. So f prime of pi over 2. I get cosine of pi over 2. And then times negative sine of pi over 2. All right, so this is cosine of, we already determined that cosine of pi over 2 is 0. So now we want the cosine of 0. The cosine of 0 is 1. And then times negative sine of pi over 2. Sine of pi over 2 is also 1. So my slope is 1 times negative 1, which of course is negative 1. So I can plug everything in. So I get y minus the y value, which comes out to be 0, equals the slope, and then times x minus the x value. So now normally I wouldn't say that you need to get out of point slope form. This one would probably be pretty easy because it's just a 0 on the left, and then I could distribute the negative. So this is a very, very simple change in a slope-intercept form, but again, if you are good with this, that is totally fine. Okay, last one. Find the points at which f of x equals x plus 1 over x minus 1 to the fourth has a horizontal tangent line. So remember, horizontal tangent line means you've got a slope of 0. So we're looking for all the places where f prime equals 0. So we're going to start by taking the derivative and then setting it equal to 0. So f prime, my outside function is quantity to the fourth. So for my power rule, I bring the 4 out front, leave my nested function right where it is, drop the power down to 3, and then I need to multiply by the derivative of the nested function. So I'm going to do a little side work over here to do my quotient rule. So high is x plus 1, low is x minus 1, d high, these are both just linear functions. The derivative of the numerator is 1, the derivative of the denominator is 1. So let's combine these all up. So for the derivative of the nested function, I have low d high, which is just the quantity x minus 1, minus high d low, which is the quantity x plus 1, and then all of that over low, so x minus 1, quantity squared. So this f prime is running into things. Let's get this cleaned up. So in the numerator, I have an x minus x, which cancels. I have a negative 1 minus 1, which gives me a negative 2. So here's where I'm at so far. So then times a negative 2 over an x minus 1 quantity squared. So here's what I've got. The 4 times the negative 2 gives me a negative 8 out front. Then I have 3 copies of x plus 1. And then over here I have 3 copies of x minus 1 times 2 more copies of x minus 1. So I have x minus 1 to the 5th. So now I want to know where that's equal to 0. So I want to set that equal to 0. So that is my last step. So basically, if I want to know when that's equal to 0, I only care when the numerator is 0. If the denominator is 0, it's undefined, which is not what I'm looking for. I want a horizontal tangent line, which means I just set the numerator equal to 0. So when I set the numerator equal to 0, first of all, I can divide both sides by negative 8. So if I divide both sides by negative 8, what essentially happens is that the negative 8's just cancel, because 0 divided by negative 8 is still 0. And I have x plus 1 cubed equals 0. Then I could take the cube root of both sides, but of course the cube root of 0 is still just 0. So I'm taking x plus 1 and I'm setting it equal to 0. And so I get an answer of x equals negative 1. So if I were to look at this graph, negative 1 would have the only horizontal tangent line. All right, so like I said, we'll pick up with the second half of these notes tomorrow.